Well, good morning, everyone. It's time to kick off our big first event for this year. First of all, can we all give ourselves a round of applause for making it through 2 miserable years of this pandemic? Let's just give it a... I will admit there was a point last year when I felt, oh my God, am I gonna see people in a room ever again? That was looking pretty bleak. And I'm so glad that we've progressed past that point, and we are at a point where now we can meet and greet each other and shake our hands and listen to young speakers speak today. So thank you very much for taking time off your schedules to be here. Really means a lot to the department and to me personally, because when you launch an event like this, you are taking up so many people's time. You know, our staff have been working pretty much around the clock for over a month now to put various things together. And then, you know, faculty taking time to prepare the students and get their research talks done and things like that. And so when you put these kinds of things, you know, yes, personal ego says we should do this as EME, but then you also have to be very cognizant of the fact that you are taking up a lot of time for a lot of people. And so when I see so many people in the room and people filing in, it makes me feel really good. It's an occasion for us to really celebrate all our accomplishments. You know, we have fantastic graduate students who, despite the 2 years of shutdown, near shutdown, progressed through their research and did things that, you know, and frankly, none of us thought would be possible, you know, when at the start of the COVID, you know, of the pandemic, the shutdown. And so we are really here to celebrate, you know, all those accomplishments. We have added some really top-notch new faculty members, and you're going to hear from them in, you know, earlier this afternoon. And then we'll culminate with a panel discussion on topics that are on everybody's mind: energy transition, where are we going to get the resources for this transition? Very important topics, and you're going to hear a panel about it. And then I don't know if you have a chance, walk by the room on the corner there and you see the posters and the technical content on the posters. It's just mind-boggling, you know, the kind of the breadth of research that's happening in this department. So I hope you'll all enjoy it. And then we can talk more over lunch and over dinner and over the next few weeks and months. And we're very interested to hear your thoughts on how we really can make this even better, you know, in the next version of this kind of event. So without much ado, I know that we are on a very tight timeline today. So I'll like to introduce Professor Eugene Morgan, who's going to be the moderator for this first session. Dr. Morgan is the associate head for undergraduate studies in our department. He's also a top-notch researcher in the area of geoengineering, of geosystems engineering, petroleum engineering, call it what you may. So Eugene, the floor is all yours.
Thank you, Sanjay. Thank you. Yes, so we have an excellent lineup of current PhD students in the department, 6 of them, starting with Amir Eskanlou, who would like to come down. So Amir is currently doing his PhD in energy and mineral engineering with a doctoral minor on computational materials at Penn State. He started in August 2021. His research interests include froth flotation, surface chemistry, modeling and optimization, and molecular modeling. Amir's research at Penn State is on the bioactivity of the ultrafine particles. And let's see, how do we? And so, Amir, the floor is yours.
Good morning, EME. Thank you, Dr. Morgan. I'm so happy to be here. My name is Amir Eskanlou, and today I will talk to you about atomistic insights into surface oxidation of pyrite and quartz, implications for ultrafine particle toxicity. So let's first talk about toxicity. Toxicity, when in construction and mining areas, the production of ultrafine particles is kind of unavoidable. These particles, when are exposed to the atmosphere, they interact with water and oxygen molecules in the atmosphere, and their surface get altered. They get surface alteration. And as a result of this surface alteration, some free radicals, typically hydroxyl radical, these radicals are formed on the surface of these particles. These free radicals are the molecules that are missing an electron. They are kind of electron thirsty molecules. And then when these particles we inhale them into our lung, these radicals on the surface of these particles interact aggressively with the tissues of our lung and then bring about lung inflammation. And then in the long term, some serious diseases such as lung cancer. So to address this problem, starting August 21, 2021, Penn State and NIOSH started a project called Reduction or Elimination of Coal Mining Related Respirable Dust Toxicity by Selection and Proper Application of Dust Control Additives. So quartz and pyrite are the main particles, the mineral particles that compose the dust in mining area. We have coal itself, we have clays, we have quartz, and we have pyrite. But in this study, we focus on quartz and pyrite. Our perception on quartz and pyrites, on the quartz surface, we know that when quartz surface get altered, we have the formation of free silanols, and then these surface siloxanes interact, get hydroxylated, and we have isolated silanol or nearly free silanols, or geminal silanol and vicinal silanols. And then on the surface of pyrite, when it interacts with, for example, oxygen molecule, the ferric iron, the ferrous iron oxidizes into ferric iron, and then this ferric iron, as a result of this ferric iron interaction with quartz, the pyrite surface, we have the production of hydrogen peroxide. This hydrogen peroxide interacts, then re-interacts aggressively with mineral surface and brings about the formation of hydroxyl radicals. So the question is how quartz and pyrite surface oxidation results in the formation of the free radicals. This is not a new question. This has been there for decades, and many researchers have done a great job on addressing this question. But there is kind of, they are not unanimous in responding to this question. And in this study, we want to see how we can bring all these results together and also do a fundamental quantum chemistry study to see what happens on the surface of these particles. So the approach is relying on the electronic structure of these particles. By calculating the electronic structure of this material, we can understand their behavior in atmosphere and when they interact with water and oxygen molecules in atmosphere. So the objective is gaining atomistic insights into quartz and pyrite surface oxidation. This is important because this formation of free radicals as a result of surface alteration brings about the bioactivity of these particles. An approach is ab initio molecular dynamics simulation using quantum mechanics. So for our simulation, we used 100 pyrite surface and also 001 surface of quartz, and they interacted with water molecule, oxygen molecules, and then the results is we ran the simulations for about 5 picoseconds, which is 5,000 femtoseconds or 5,000 electronic steps. And then after obtaining the ultimate geometry, we did the ground state DFT calculation to find the ground state energy of these geometries. And then compared the interaction energies, both for silica and pyrite, different when they interact with water molecule and also when they interact with oxygen molecules. And then in conclusion, the adsorption of water molecule on the surface of quartz is slightly more thermodynamically favorable than oxygen. Such interactions entail the formation of SiOH, the free silanol, and hydroxyl radicals and peroxyl defects. If you ask what is peroxyl defects, this is peroxyl defects. This is peroxyl defects as a result of oxygen interaction with a quartz surface. And then we have on the surface of pyrite, the adsorption of oxygen is more thermodynamically favorable than water, which means that your surface alteration when in atmosphere for pyrite is more dominantly done by oxygen than water molecules. So pyrite surface oxidation is due mainly to the presence of oxygen molecules. Such interactions lead to the formation of Fe2 plus OH2, Fe3 plus O2 minus, and Fe3 plus OH minus, Fe3 plus OOH minus, and oxygen sulfur interaction, and then the formation of hydroxyl radicals. So this is our conclusions for this study. You can see from here that on the surface of pyrite, whenever we have oxygen, the oxidation state of iron changes from ferrous iron to ferric iron. And the production of this ferric iron entails the formation of these free radicals on the surface. This shows the importance of oxygen interaction with the surface of pyrite and the contribution of oxygen as an oxidant. So thank you so much. And if you have any questions, I will be happy to answer. Yes, sir.
You said it was slightly more thermodynamically favorable. Is that right? They both are thermodynamically favorable?
They are.
Yeah, let me give you the mic there. Yeah, really great talk. Thank you. So my question is about you said they're both thermodynamically favorable. Do you have any insights into the kinetics to figure out if one will actually happen faster than the other?
We haven't done the, thank you so much for your question, great question. We haven't done the kinetics study on that yet. In this study, we just focused on the competition of these water and oxygen molecules on the alteration or for the alteration of this mineral particle surface, surface alteration of these mineral particles. And then we compared the interaction energies by finding the DFT ground state energy of the ultimate geometries after doing the simulations to compare them and figure out which state, which interaction is more stable thermodynamically than the other one. For kinetics, we will look at in the future. Thank you.
Thank you for the great talk. My question was, do we know the reason why these particles cause inflammation, or by what mechanism these particles cause inflammation?
Yes, yes. Thank you so much for your question. Yeah, when we inhale these particles into our lung, these particles, as a result of their surface alteration, these particles have free radicals, hydroxyl radicals on their surface. And these free radicals are the molecules that are missing an electron, which means that they look for an interaction to get stabilized. They are electron thirsty. They are reaction thirsty. They are so aggressive. So then when these particles are inhaled into lung, these particles sit on in our lung, and then these free radicals interact with these tissues aggressively with these tissues and make these tissues free radicals as well. And these tissues get free radicals as well because they lose an electron to that molecule and they get themselves a free radical, become a free radical. And when this happens in lung becomes inflamed. And this inflammation brings about lung cancer and the other serious problems.
Thank you for your presentation. Question about the computation portion. I think you mentioned you ran your simulation for 5 picoseconds or something like that. I'm just curious the rationale for that particular based on that time.
Yes. Yes, we can. We use VASP code for our DFT calculations and for our molecular dynamic simulations. You can go up to 100 picoseconds in your simulation. But because of the computation limits and the resources that we have and the time, each of these calculations take about 2 weeks to get done. So with considering all these limitations, we ran some primary test calculations to see at what step or picoseconds we can reach an ultimate geometry, after which we don't have much difference. Then after that, we picked, okay, 5 maybe is a reasonable or rational time to go and then stop. This was what we, because of limitations and also looking at different results to see where we can get the ultimate geometry.
How can you utilize the research results to protect our minds? Because this research is all geared towards how we can prevent our minds from illness.
Yes, very great question. Yes, the results of this study, this is a research project which is focused on the elimination or reduction of the toxicity of this particulate matters in mining area. At this stage, we want to first fundamentally understand why these free radicals are formed and where they come from. Under what mechanism are they formed at very atomistic level, very fundamental level, and then reason up from there to solve the main question, which is the elimination or reduction of the toxicity. We will use some reagents to mask or suppress the production of these radicals by suppressing or masking the surface alteration of these particles. But from here, we understand how they happen. And then we will reason up and then build up on our results from fundamental results and do the fundamental other experimental studies. We will use spectropolarimetry to monitor the formation of these free radicals, and then some reagents to treat our particles to see how we can mask the surface alteration of these particles, and thereupon the formation of free radicals.
Great presentation. I would just try and broaden the viewpoint a little bit. You talked about coal mining related respirable dust toxicity. I would say that sand handling, quartz in hydraulic fracturing operations, for instance, has a significant impact on those who are handling that. And certainly this kind of research is very helpful for that.
Thank you so much. Yeah, appreciate your comment. Thank you.
Another round of applause for me.
Leiyu is got his BS in Environmental Science and Engineering at the South University of Science and Technology of China. His research has been published in the journals Science of the Total Environment and Environmental Science and Technology. His research interests include biological wastewater treatment, water reuse, nutrient and energy recovery, and environmental sustainability. So without further ado, Leiyu.
Thank you. Hello, everyone. I'm Leiyu, and I'm from Dr. Wang's group. So today I will give you a presentation about the redirection of organic compounds from the wastewater by the high-rate contact stabilization process. So we know that in the wastewater, it contains the organic carbon, nitrogen, and phosphorus, and we need to remove them from it. In this process, the aeration is used for the organic compounds removal and the nitrification. And in the wastewater treatment, it will consume the 40 to 60% of the energy in the wastewater treatment. And every year in the US, wastewater treatment process will use 30.2 billion kilowatt an hour every year. So for one thing, we hope we can reduce those energy demand in the wastewater treatment process. And for another thing, it will produce the carbon dioxide and the nitrous oxide in this process. Both of them is the greenhouse. So we also hope we can reduce the greenhouse emission in the wastewater treatment process. So based on this, the absorption bio-oxidation process was proposed to reduce this energy demand. It have two stages. In the A stage, is belong to the organic carbon capture. So it will capture the organic carbon by the different technicals like the primary settling and the chemical enhanced primary treatment process and the high rate active sludge process. And this project used the high rate contact stabilization process. After remove the organic carbon, and in the B stage, it belongs to the natural removal. For the natural removal, they plan to use the partial nitrification and the anomorphs. About the conventional biological natural removal, it's use the nitrification and denitrification process. This process will need the oxygen and it will transfer the organic carbon to the carbon dioxide. So it's energy intensive. And we hope we can develop the partial nitrification and anomorphs process. So this process is the anaerobic environment. So it can reduce the aeration up to the 60%. And for another things, there is no organic carbon addition is needed. So if we can successful to develop it, it will save energy in it. So let's look at these fingers. It's just like this. In this part, the effluent contains the organic compound and the nitrogen compound. And the microbles in the wastewater will capture the carbon as much as they can, surrounded the storage their food. And the left is the nitrogen compound will flow out to the B stage. And after settle down, the microbe in the sludge, with the concentrated organic carbon can be used for the anaerobic digestion or another upgrade technicals. It can produce the biogas and bioplastic or other value-added productions. It's just like these fingers. In the A stage, the captured organic carbon transferred to the energy by the anaerobic digestion or other technicals. In this process, we gain the energy. And in the B stage, since we reduce the aeration demand, so in the B stage, we can save some energy. So one increase and one decrease. So we hope we can achieve the transfer from the energy negative to the energy neutral or the positive in the wastewater treatment process. In this project, we use the high rate contact stabilization process. It's a very interesting method since it have two tanks. One is the contact tank, and the effluent would flow into this tank. It's something like just provide the food to the microbes. So this is a phased environment. And in the stabilization tank, there is no food, and we will provide the aeration, a little aeration in there, and it's something like the famine environment. So we quickly shape those two environments, the phased and famine. So under this quickly shaped, we create an extreme environment for the microbes. With the environmental pressure, the natural will select those microbes can be capture the organic carbon, capture the food very, very fast. So we can achieve the higher carbon capture efficiency in the relative short time. Previous research got the higher carbon capture efficiency and the energy recovery efficiency. So in this project, we hope we can develop the relationship between the dissolved oxygen and the solids retention time. That means the microbes retained in the reactors. And about the carbon capture efficiency and the organic carbon efficiency. And we also run the 16S, do some biological analysis about it. And we also hope to do the anaerobic digestibility of the sludge. So we mimic this process with the sequencing batch reactors. And this is a timeline for the one cycle. We set up the operational conditions. First is we set up different aeration conditions. The stabilization aeration means we provide the aeration in the stabilization tank And the CSA means will provide the aeration in the contact and stabilization phase. We also set up the different solid retention time and 3 days, 2 days, and 1.3 days. So finally, we got a 6 set of the operational conditions. Here is the result about the organic matters removal efficiency. With the decrease of the solid retention time, the removal efficiency also would be decreased. But this project, our aim is not to get the highest removal efficiency. So this finger is more important than previous. We hope we can got the higher carbon capture efficiency. So the red column means the carbon oxidized, and the carbon oxidized means the transfer to the carbon dioxide. So in the red column, the COD oxidation ratio would be increased with the increase of the SRT. It's a very clear trend. And for the orange part is the carbon captured. We hope we can increase this part. And in this project, we got the highest carbon capture efficiency is in the 1.3 days, and the 42% in the SA conditions, and the 47% in the CSA conditions. And the bottom two column is the carbon not be captured, and it will flow out as an effluent. We also detect the production of the excellular polymetric substance, the EPS production. The EPS is the one kind of the directly production from the carbon capture. So it's just like the bacterial storage food surrounding the. So the decrease of the SRT, you can see that in this finger, would increase the EPS production. So it means the low SRT can produce the higher EPS production. And about the anaerobic digestion, we run the two set of the operational conditions, and under the 1.3 days SRT, the highest machine production is 167 milliliter per gram VS. And if we compare with the yellow line, this is sludge from the wastewater treatment plant. We can say that all the HiCS sludge have a higher potential, a higher energy recovery potential than the commonly active sludge. And this is a 16S RNA community analysis. And if we compare the different solid retention time, we can get the higher SRT has a higher microbial diversity. And if we compare the different aeration conditions, and we will find that it have the different dominated genus. The different color means the different dominated genus, and I pointed name in there. And this is our B process, the next step, and it's still in progress. And we hope we can about the nitrogen removal. And we hope we can get the good result about this part. So this is our take-home message. We explore the relationship between the oxidation and the And this is our acknowledgement. So that's all. Any questions about it?
Thank you. I'm curious about when you talk about the diversity of the microbial community.
Mm-hmm.
How easy is it to actually change that out in practice? Something that can be changed.
You mean why the microbial would be changed in under different conditions?
Well, I'm talking about in practice, and if this is a commercially run process, is it easy or difficult to actually change the microbial community at large scales?
Sometimes it's not very easy to change yeah, change it, just give them, sometimes we give them the different environmental pressure to change the different communities. Yeah.
Thank you, for the great talk. I just wanted to ask you, is the methane gas production higher than, let's say, biogas plant? If I were to do a biogas,
Sorry?
a biogas plant, if I were to make a biogas plant, would the amount of methane gas I would produce there lower than the highest you are taking here?
Oh, yeah, so
Here is the biogas and on the different stations, and for the green line, you have to the one station, Assimilation, 107. But that is, the 58 is for biogas, like anaerobic digestion.
yeah, yeah, our need how to digestion our any production is question. But our production is eventually the evidence that in this experiment, our science question about the digestion is the same.
Great, another round of applause for Leiyu.
So James got his BS in Environmental Systems Engineering with us here at Penn State. He also got his Associate of Arts in Liberal Studies, graduating magna cum laude at Montgomery County Community College. His research is focused on carbon materials, graphitization, and nanocarbons. So without further ado, James Heim.
Hi, I'm James Heim, and my project is process development to prototype fabrication coupled with techno-economic analysis and market survey of coal-based bricks and blocks. Our project's funded by the National Energy Technology Laboratory, and the primary focus of this is to rehabilitate coal towns that have been decimated with poverty to find new uses for coal. The primary investigator is Dr. Randy Vanderwall. And our team members are myself, James Heim, Schober International, ADI Analytics, or International, or yeah, Analytics, and Blaszak Coal Corporation. So just some background, coal and coal byproducts can be incorporated into novel materials for the purpose of improving performance, decreasing cost, or both. Coal-derived building materials should possess equivalent performance at a lower price or possess properties that are superior to existing building materials. Economic assessment must be contrasted with potential markets, associated performance, and required scale. New technologies and processes are needed to produce novel building materials from coal. So just an overview, the United States coal value chain can be extended by manufacturing coal products directly from coal instead of using derived feedstocks. Coal-based construction materials will contribute to cleaner energy. If one considers that a traditional clay brick is fired at 1600 degrees F to 2400 degrees F for 10 to 40 hours, and our bricks, all we do is melt the thermoplastic binder. So they are fired between 300 and 500 F for about a half hour. So this project will evaluate the ability of coal-based bricks and blocks to compete on price, quality, identifying competitive strengths and limitations. So this is just a process schematic following the material flow. And I would like to preface this with saying that it would be ideal for these manufacturing plants to be positioned right alongside of a coal mine or in the same town to cut down on transportation pollution and transportation costs. But on the left, we have the coal will be crushed, it'll be milled and then screened, stored, and then it would be mixed with either a thermoplastic or a thermoset binder, or mixed, and then it would be either compression molded or extruded. So on the bottom, you see variable form factors through extrusion for our bricks. The form factors will be determined on the use and strength. So this just gives you an idea of our design of experiments. The factors, we're employing a fractional factorial design matrix. The factors are the weight percent of the binder, the proportions of anthracite size fractions, and carbon black additive amounts. Our responses are compressive strength, permeability, density, and hardness. So for economic and commercialization assessment, our techno-economic analysis, this economic analysis will include estimating capital costs and operating costs over the equipment service life. The TEA analysis will reflect the reduced energy costs for coal-based bricks and blocks and reduction in CO2 emissions. Our market survey for coal-based bricks and blocks and price analysis, the survey will benchmark CBB mechanical and material properties relative to commercial brick and block requirements. The technology gap assessment will be identifying required R&D for scale up and commercialization. So this is just an idea of some of the experiments that we've run so far to get to where we are today. So on the left, you see a graph or compressive strength comparison of polypropylene bricks that has 3 different test matrices in it. The first being the coal formulation strength series in blue. The second being the plastic particle size strength series in green. This strength series was for dry mixing of the raw materials and hot press molding it. We wanted to figure out the smallest particle size of the smallest plastic particle size, such that each coal particle was completely covered on all sides with a plastic binder upon being melted and compressed. And then in the orange, we have the material comparison series. In this, we wanted to test the wettability of the coal surface and the thermoplastic. So we compared it to analogous materials as the aggregate, such as glass and sand, and we found that the coal won out. So on the right, we have the compressive strength series of polystyrene loading. We needed to figure out the nominal loading of thermoplastic, before which we were testing basically the plastic buildup between coal particles, the shear force rather than the interaction between the coal and the thermoplastic. So this just gives you an idea of some of the material characterization we're doing. We're doing porosity, permeability, density, and microscopic structures. You can see on the top figure 6, the contact angle showing the hydrophobicity of various virgin and PCR thermoplastic and anthracite composites, which is a huge advantage when you consider that most of the degradation to cementous materials and bricks are from water ingress and the freeze-thaw cycle, at least in this area. So figure 7 shows how we analyze the interaction between the coal particles and the plastic. We use SEM to see how they're attaching to one another and if there's void spaces. So what we've accomplished, we've completed the DOE matrix for particle size, loading, and plastics. We've identified optimal plastic binder forms according to appropriate applications. We've demonstrated fabrication of hot press molding. We validated extrusion feasibility for brick formulations. And The best part about this is coal-based bricks and blocks. We've exceeded the compressive strength relative to the standards of conventional clay bricks. So a conventional clay bricks has a compressive strength of 6,700 PSI. And if I go back to this graph, this is just one series. We've made 100 or more bricks at this point with different thermoplastic binders. But you can see right here that there's 3 or more coal bricks formulations that have exceeded the 6,700 mark. So what's next? Fabrication and testing of half-scale brick by extrusion. Techno-economic analysis, including CapEx and OpEx. Conducting market survey for consumer and construction uses. Performing a technology gap analysis comparing market requirements to CBB performance. The key advantages, again, of our bricks are the CBB fabrication offers sustainable energy savings compared to clay bricks, half a day to a day and a half of firing compared to 30 minutes at a reduced temperature. The CBBs are roughly half the weight of clay bricks and of comparable strength. If you consider most of the people that get hired to, put retaining walls at people's houses, the majority of that cost is from renting equipment and the labor. And so this would allow for an interlocking design, for retaining walls. A consumer could just go to Home Depot, Lowe's, buy these bricks. They could transport them in their car and build it themselves. So the technical advantages include impermeability and corrosive intolerance. Thank you.
Very interesting presentation, thank you. Bricks over time, you mentioned the weather like we have in the Appalachian Basin with freeze-thaw. Bricks over time will fall. The polypropylene binder or molding agent that you use in coal, do you believe that that'll keep coal from falling or from chipping away over time?
That's a good question. I'm not so sure of the answer of that, but we've also looked into, for bricks that are exposed to the outside, chemical resistance, should they be on the ground, acid mine or acid runoff from fertilizers, stuff like that. And then also UV degradation is a big concern. That's why one of our top choice is nylon 6,6, which has excellent chemical resistance and UV degradation. It doesn't have high UV degradation. Our second choice was polypropylene. Yeah.
Very nice presentation.
Thank you.
Number one is that I saw the name of anthracite. So is it the only one we're considering? Because anthracite is dying almost in the industry. Are you thinking about the bigger industry like the bioindustry that was thinking inside? And the second question is that a good one is like say if it is produced near the mine themselves, they use a huge amount of blocks to deal with the degradation, stopping and stuff, the market right to it. But in the outside world, when you are using like the how much is this material being tasted for being this combustible themselves? Like I heard about the physical testing and all that. How much is the whether causing fire or explosion? But I'm sure you're taking that.
Right. So I'll start with your second question first. So it would depend on the application. Another reason that we chose nylon 6,6 as a binder is because it has a UL rating of 94, which means that it'll extinguish within 15 seconds of ignition. A lot of literature cites the combustion of coal between a range of 300 C and 600 C, more so to the 300 range. So we feel that, if the application was for houses and with other building materials that have a much higher UL rating than 94, that the combustion wouldn't be a problem. I'm sorry, what was your first question? Right, so actually we're just focused on the anthracite given the strength of it and the hardness. And also the fact that it has the lowest amount of heavy metals in it. We thought it would be a good choice. That's a great question. Thank you. I meant to touch on that, but that's where this whole project started. It started with repurpose and reuse. Repurpose coal and reuse the waste plastic, which in theory, it sounds like an excellent, an excellent marriage between the two. But in practice, the more that the plastic is processed, the more it thermally degrades, and that lowers the physical properties of the plastic. So if we're going for ultimate strength as a load-bearing wall, we would need to probably use more virgin materials. The company that we're partnered with, Aviant Technologies, a huge plastic manufacturer, they have products called Resound, and the Resound means they incorporate a certain percentage of post-consumer recycled material into their, sellable, they mix it in with their virgin and PCR. We found that because it undergoes extra processes, the physical properties are lower, and it also is a lot more expensive. So we kind of evolved from a PCR focus to more of a virgin focus, but that is only because we're still in a phase 1 of this project. We would like to find a way to incorporate the PCR materials, be it just, coating it with them and having the virgin actually be the binder to create structural integrity, or, if we can incorporate a certain amount according to the application. So if they're just pavers, they're going around a flower bed, of course, PCR all the way. We could coat it with nylon just so that, it's protected, has UV protection, or we can even mix carbon black in it for UV protection. So it really just depends on the application and what markets seem to, be most interested in this in the beginning.
So Shams Joon did his master's in our department in energy and mineral engineering with a thesis on velocity model calibration using distributed acoustic sensors and sparse geophones. Before that, he did a dual major in geosciences and also petroleum and natural gas engineering at Penn State with a minor in geophysics. His research interests include geologic carbon storage, petrophysics, and seismology. So Shams, you have the floor.
Thank you, Eugene, for the introduction. As he mentioned, I've been here since my undergrad, so 2013. So as my academic journey at Penn State comes to conclusion, it's a pleasure to present my research among you all. Today, I'll be talking about a optimization framework to optimize the placement of monitoring wells and sensor types at geological carbon storage sites. Before I even delve into the methodology, I think it's important to take a step back and think about where geological carbon storage fits into this this carbon storage, carbon mitigation strategies that are available to us today. So the most recent IPCC report that came out suggested that for every 1,000 gigatons of CO2 that's emitted into the atmosphere, the global temperature rises by about 0.5 degrees Celsius. With emissions around 40 gigatons CO2 per year right now, this means that by the time we reach 2050, the Earth would be 0.5 degree warmer. And if we look historically from the 1870s, roughly 2,000 gigatons of CO2 has been emitted into the atmosphere. And with geological carbon storage capacities ranging from 8,000 to 55,000 gigatons of CO2, from a macroscopic material balance perspective, we could essentially sequester all the CO2 that's been emitted and still have room to offset future emissions. And while geological carbon storage provides an innovative solution to mitigate the anthropogenic emissions, one of the primary risks associated with these type of projects is that the CO2 can unexpectedly migrate and go undetected. And that's why modern tools are used to infer how the CO2 plume is stored and how it's changing over time, and is often required by EPA regulations. And these sensors or tools can be deployed in the atmosphere, near the surface, in the subsurface, and perhaps more recently, something called an intelligent monitoring design, consisting of multiple observations, multiple tools combined together to infer changes and come up with real-time predictions. One type of intelligent monitoring tool that I focus in my research includes continuous active source seismic monitoring, or CASM, with bubble pressure sensors. CASM is a continuous cross-field seismic survey. What that means is that a seismic source is embedded at the injection well, and the source constantly emits seismic energy, which is recorded by an array of receivers at a monitoring well. And as we inject CO2 into the subsurface and the CO2 displaces the in-situ fluids, these seismic responses change. And these changes can be indirectly inferred to understand how the CO2 is moving spatially and over time. In a paper that we recently published, we actually go into more details as to how you would do that and how you could use data assimilation and rock physics to answer the question of how my CO2 plume is moving over time and space. And while the methodology is quite complicated, I think it's very well explained through a schematic. What we essentially do is instead of having a singular reservoir model, we use an ensemble of models. These models have varying initial conditions, initial parameters like permeability and porosity, and we combine them and we propagate them forward in time using a numerical simulator. And because these are different initial conditions and varying initial properties, they produce different forecasts. These forecasts are then compared to the physical observations that we're collecting at the field site. So in this case, we take the raw CASM data, use seismic inversion, come up with seismic velocity and attenuation observations, add them to our pressure monitoring sensors, and compare them to the forecast that we just generated. We do this by using an ensemble common filter. And what this common filter essentially does is it compares our confidence we have in our forecasted ensembles and compares that to the measurement noise that we assume in our measurements. And using a variance minimizing framework, comes up with a state estimate that has a smaller uncertainty as compared to the independent forecast or our measurements. The state estimate then feeds back into our loop as the initial ensemble, and the cycle is carried out over and over again as more observations are made available to us. And what we saw from this work was that having observations that cover a large amount of area and are sampled frequently help reduce the uncertainty the most. Furthermore, combining different types of observations helps us also reduce this uncertainty. One of the questions that came out of this research, and we hope to answer with the same framework, is that as we're injecting the CO2 and we're placing these monitoring wells, how can we optimize where these monitoring wells are placed in a way that will reduce the uncertainty associated with our predictions? One way to do this would be using perhaps a brute force approach, sampling every possible scenario, every observation well, and finding out which one gives you the least amount of error. But that can be quite computationally expensive and can take a lot of time. So we came up with a new methodology that can be perhaps more computationally tractable. We start off with an initial monitoring design that we assume. Here, I assume that the only measurements we have are pressure sensor measurements at the wellbore, and we simulate the CO2 evolution by simulating these observations. To the left, I show how the CO2 plume and pressure evolve over time. To the right, I show how the standard deviations as calculated by those ensembles are visualized over time. What we see is that these standard deviations vary in location, scale, and magnitude over time. So we could perhaps average them over time, as shown here, for both CO2 saturation and pressure, and identify these warm regions where we have the highest amount of uncertainty. This allows us to reduce the number of simulations we would run for monitoring wells by coming up with smaller number of scenarios. So here we select 5 scenarios, 3 from our CO2 saturation map, 2 from our pressure map, to simulate and identify which one would produce the least amount of uncertainty. To do this and compare how each monitoring scenario is working compared to each other, what we do is we compare the covariances associated with our pre-existing monitoring design with our proposed monitoring design. And we do this by taking a difference between the covariances of the two for each monitoring scenario. And to come up with a singular metric known as the impact factor, we just take the trace of the covariance difference. And the idea is that the scenario that produces the highest amount of difference between this metric would be deemed the most ideal candidate location for placing a monitoring well. So of the 5 scenarios that we ran, we plotted the impact factor for CO2 saturation and pressure for all 5 scenarios. And what we observe is that observation well 3 and 2 produce the highest impact factor or the least amount of uncertainty when observations are collected from these 2 monitoring wells. The same trend is observed in the pressure heat map, where we observe that observation well 2 produces the highest impact and would be considered the ideal location for drilling a new monitoring well. Some of the concluding remarks from this work are that one, that having observation and monitoring tools that provide high sampling rate temporally and cover a large spatial area are beneficial when you're trying to study the subsurface dynamics of a geological carbon storage site. Using an ensembled space instead of the brute force approach allows for a computationally tractable solution to the question that we're asking, while honoring the underlying physics by incorporating numerical simulations. The novelty of this work is that by optimizing where we place monitoring wells, we can improve how we understand the subsurface. Since we're working with systems that we can't physically see or touch, we often have to rely on predictions. So having an optimization framework is beneficial from a perspective of cost and risk. And moving forward, the idea is to use this framework and test it out on more complex geometries and reservoirs, and perhaps incorporate it to study the risk-based value added of refurbishing abandoned wells at these kind of geological carbon storage sites. With that, that concludes my presentation. I'll be happy to answer any questions.
Thank you, very important work. I was wondering, have you given any thoughts to the economically optimal number of systems you might place? And some of the specs of the nation, so what level, what's the critical mass? What are the economic
That's a really interesting question. So identifying how many monitoring wells you should be drilling and how many sensors you should be deploying is kind of a heuristic scenario. The operator has to make that decision, and the EPA has to dictate those guidelines to come up with the ideal solution. I think it's hard to answer that question from a research perspective. I think the research question would be designed more towards the policy aspect of that scenario.
That was a very nice presentation. The usual question about ensemble-based methods, right? There are severe restrictions related to toxicity and also related to the fact that there can be multiple sensors that have confounded information and just without the trace of
So yes, with ensemble-based methods, the idea of Gaussian assumption is predominant. By using an ensemble and preserving that non-Gaussian trend in our forecast allows us to answer some of those questions without defying like the underlying assumptions of the model. And perhaps like deducing the covariances to identify where we place these monitoring wells is suboptimal on certain ways, but it does provide a meaningful solution to a question without actually deploying the sensors in the first place, right? So it could be a pre-processing subroutine that you carry out before you actually drill the well. And I think that's one of the benefits of this work.
So Sean Okonsky is a PhD candidate in chemical engineering at Penn State, advised by Dr. Hilal Azgi Toraman in our department. Okonsky's research is focused on gaining a mechanistic understanding of how catalysts help to upgrade pyrolysis vapors from mixed plastic waste to valuable chemicals. He got his BS in chemical and biological engineering at the University of Colorado Boulder. And he also received the Energy Environmental Sustainability Laboratories Green Award in 2021. Sean, take it away.
Thank you very much, Dr. Morgan, for the introduction. I'm just going to start the timer so I don't go over. And thank you very much for inviting me to talk at this research showcase today. This is my first time presenting my research in person, so I'm very grateful for this opportunity. So today I will be talking about the research that we have conducted related to the catalytic co-pyrolysis of LDPE and PET with multiple zeolite cathodes. So why we are interested in this research has to do with plastic waste, and PET is one form of plastic waste that contributes to almost 4 million metric tons per year of waste every single year. And of the PET that is recycled, most of this recycled PET ends up as fibers in either carpet or clothing. And this is known to leach microplastics into our waterways. In addition to PET, there is a class of polymers called polyolefins, and these contribute a huge amount of waste every year and have very low recycling rates. So the combination of these two polymers contribute to almost 22 million metric tons per year of waste that can end up in our landfills, which can then end up in our environments or are incinerated, which then leads to the pollution of our atmosphere. And rather than treating this very large volume of hydrocarbons as a waste, we can see them as a valuable feedstock if we treat them with pyrolysis. And pyrolysis is a clean technique which can convert these polymers by heating them in the absence of air. And it can convert these feedstocks to valuable fuels and chemicals. If a catalyst is added in the pyrolysis process, this catalyst can help to guide what products are formed and can also decrease the temperature needed to convert these feedstocks. So to do some research in this field, we looked at two polymers, LDPE, which is representative of polyolefins, and PET. And we looked at 3 different commonly used zeolite catalysts. And what we wanted to do is to see the effect of these zeolite catalysts on both the individual pyrolysis of these polymers and the one-to-one co-pyrolysis of these polymers. And how we did this is using 2 different instrumental techniques. The first is called thermogravimetric analysis, TGA for short. And what this measures is at what temperature is the polymer degrading into pyrolysis vapors. The other instrumental technique we used is what is called the pyroprobe GCMS. And this is able to identify the pyrolysis products which are formed and is able to quantify the relative amount of these products which are formed during our pyrolysis. And so the first results of this work I want to show you is the results from the TGA. So on the top, we can see the TGA curve for LDPE. And what we are able to see is that this the addition of the catalyst greatly decreases the decomposition temperature of this LDPE. And when we look down below for the PET, what we see is that adding the catalyst does not decrease the decomposition temperature nearly as much. And another thing that we observe with PET is that there is a very high solid residual. And this is due to PET being a charring polymer. And we also noticed that the catalyst of the H beta and the HY result in a much larger solid residual, which is made up of both the non-catalytic char and the catalytic coke. And we believe this is due to the H beta and HY having the larger pore size than this HCSM5 catalyst. So now that we have done the individual pyrolysis of these polymers, what we are able to do is calculate an additive curve. So this is the curve that we would expect to see during the co-pyrolysis. And this is the curve shown in red for these figures. Then we ran the actual co-pyrolysis at this 1:1 LDPE to PET ratio. And what we see is that the actual curve is not the same as this additive curve. And this shows that there is some interaction effects occurring between these two polymers during this catalytic pyrolysis. And we see that these interaction effects are similar for all of the catalysts. One that we see is that this degradation at 300 degrees C, which is corresponding to the degradation of LDPE. This is decreased in magnitude for all of the catalysts, and it is believed that this PET is delaying the degradation of the LDPE. So then what we wanted to do now that we had our TGA results is we wanted to apply kinetic modeling to these results, because if we have the kinetics, we can then more easily predict what will happen in larger reactor systems. And so we used a reaction scheme which incorporates a catalytic binding reaction. And what this allowed for was for us to actually model these interaction effects. So we only have one set of kinetic parameters for the LDPE and PET, and these parameters both work for the individual pyrolysis of the polymers and for the co-pyrolysis. And we were very excited to see that this reaction scheme, which had not been used before for the co-pyrolysis, was able to capture these interaction effects. So then moving on to the next type of experiments, we are able to see what products form during our pyrolysis. And we are able to see that which catalyst we use changes the relative amount of the products which are formed. So here we have our GCMS area percent of our various products. And we see for LDPE, the main products which are formed are the C3 to C10 paraffins and olefins. We see that the zeolite Y catalyst, which has a larger pore size, results in forming the larger paraffins and olefins in the C5 to C10 range. And this is interesting because these C5 to C10 paraffins and olefins are potential molecules which can be used for gasoline. We also see that for the aromatics, the HCSM5 forms the highest amount of these. And this is likely due to the high acidity and the shape selective nature of this catalyst. So then if we look at the main products for PET pyrolysis, we see that benzene is largely the major product. And we see that the effect of the catalyst on these oxygenated compounds, we see that HY, which has the lowest acidity of all of our catalysts, results in the highest oxygenated compounds, and HCSM5 with the highest acidity results in the lowest amount of these oxygenated compounds. We also see that the polyaromatics are highest for HCSM5. And why we believe that this is the case is because these polyaromatics are co-precursors. And we believe for the H beta and HY catalyst, what would be a polyaromatic is actually staying inside of the catalyst as it is being converted into coke. And this correlates with what we saw in our TGA results, that the H beta and HY had this highest solid residual. So now that we've done these single stream experiments for the product characterization, we were able to do the catalytic co-pyrolysis. And we were able to have compute an additive area percent. And from this, we're able to calculate what is called a synergy. And this positive synergy percent is saying that we saw a higher area percent for these products than would be expected from the single stream experiments. And what we saw was that for all of our catalysts, there is a positive synergy percent for both the alkylated benzenes and the polyaromatics. And there is a negative synergy percent for the C4 to C10 paraffins and olefins and for the benzene. So what we believe is happening is that the benzene from the PET pyrolysis is reacting with the C4 to C10 paraffins and olefins from the LDPE pyrolysis to form the higher amounts of these alkylated benzenes and polyaromatics. And we can see, if we look at our alkylated benzenes, we can see that the level of the synergy is dependent on the catalyst. We see that the HY has this very high synergy percent for alkylated benzenes, which is very beneficial because these alkylated benzenes, such as toluene, can serve as octane boosters for fuels. So to wrap up the presentation with some conclusions, the LDPE degrades at a much lower temperature in the presence of catalysts than the PET. And there was interaction effects observed during our TGA experiments, and using the reaction scheme which we employed, these interaction effects were able to be captured. And we saw the positive synergy for the alkylated benzenes and polyaromatics, and the negative synergy for benzene and C4 to C10 paraffins and olefins for all of our catalysts. And I would like to acknowledge my advisor, Professor Halal Ezgi-Torman, along with Jai Ramakrishna, a postdoc in our group, who has been a co-author on this work, and for all of the funding sources for this research. And with that, I'd like to open up the presentation for any questions.
So my question is, with the low density polyethylene, the baseline low density polyethylene versus the catalytic decomposition, you got more decomposition with catalytic, but with PX, it was the reverse, right? What is the reason for reversing that? Is there any
Yeah, so that's a very great question, and definitely something that we have been thinking about trying to explain. So we see that the PET, there's a slight decrease in the degradation temperature, but it's not nearly to the magnitude for the LDPE. And what we are thinking why this is occurring is because this PET is a much, the polymer structure is much larger than for the LDPE. So we are thinking that the PET may have a harder time entering the pores of these catalysts to enhance the degradation. One thing that we do notice is that the H beta had this highest degradation for the PET, and our H beta also had the highest external surface area. So this kind of leads us to believe that maybe the PET is degrading via the external acid sites rather than the internal acid sites of these zeolites, but that's something that we are wanting to investigate further.
And one more question. Between the PET and the catalytic decomposition, what is the reason why the catalytic is or finally like comparing to the baseline normal pyrolysis after adding catalytic, why degradation?
So I believe that what may be happening, we have a, I think if I can, there should be a slide that for this paper, we had a proposed reaction mechanism. So what we believe is happening is that there is this, this proton, and that this may be attacking this oxygen in this PET polymer, and that's what leads to this enhanced degradation.
So my question is about you mentioned solid residue, right? And I know that and Derek talked about some, but my question is, does this solid residue prevent you from as water cycles? And the second question is, if you can mention about the overall efficiency comparing the good products aspect and compared to the solid residue.
So to answer your first question, if having this solid residual resulting from the pyrolysis, is that going to essentially make it so the catalyst wouldn't work for a subsequent reaction? And that's something that we are very interested in and wanting to look into now. We didn't do that for this study. I imagine that for this PET, just these single PET pyrolysis where we form around 30% solid residual, I think that it would decrease the activity of the catalyst pretty quickly. So we're thinking maybe to look more at this co-pyrolysis where we have the LDPE, so this effective PET is smaller, and rather than maybe looking at 50% PET, we could look at 20% or 10% and see if this small amount of PET is going to deactivate our catalyst to a certain extent. And then can you repeat your second question?
About this overall efficiency over not and these numbers your main one. Time for one more question.
I was wondering why you selected LDPE as your representative polymer for polyolefin, and then how much your pyrolysis mechanism would change if you looked at other polyolefins.
Yeah, that's a very great question. That was something that we had to, all of the polyolefins, the polypropylene, high density polyethylene, low density polyethylene, these are all known to be very valuable pyrolysis feedstocks. They have a high hydrogen to carbon ratio. And we chose LDPE because we had seen in a paper that the LDPE degrades at the similar temperatures as the PET. So we thought that we would maybe be able to maximize interaction effects because of this. I believe that the LDPE and HDPE would most likely react similarly, but I think that for polypropylene and PET, there could be different interaction effects that we see, since the structure between polypropylene and LDPE are different, and their non-catalytic pyrolysis forms much different product distributions.
Today I'm going to present comprehensive two-dimensional gas chromatography method development for the pyrolysis of polypropylene. So I would like to start with a brief introduction about plastics, plastic waste, and pyrolysis. Plastics are synthetic polymers made from petrochemical feedstocks, and they have been used to replace many materials such as ceramics and metals because their duration and low cost. This part is very important because the US has produced around 35.67 million tons of plastic waste in 2018. And 75% of this plastic waste was landfill, which is a real problem here. So the most important plastics found in the plastic waste are PP, PT, and PE. And in this work, I will focus on PP. PP is a polyolefin that is widely used because it's excellent chemical and temperature resistance. In addition, PP was the most produced polymer in 2015. Talking about waste, in the US, well, the US has produced 8.15 million tons of PP in 2018. So it is important due to the lower recycling rate, it is important to propose new mechanism to recycling all this waste. And for that, we propose to work with pyrolysis. This has been proposed as an effective method to recycle plastic waste. As an overall, the temperature allows to break down the macrostructure of the polymers to form smaller molecules. As a result, the pyrolysis produces oil, gases, waxes, and char. And well, this process has some advantages, such as we can recycle mix of polymers, and also the feedstock does not require pretreatment steps. However, it is important to understand the pyrolysis process and have a full understanding of the mechanism for the pyrolysis. And in this research, we want to focus on that. So I would like to start to talk about the normal method that the pyrolysis has been researched. One-dimensional gas chromatography has been used to identify the products from the pyrolysis. However, the one-dimensional gas chromatography is an analytical technique that has different limitations, such as the co-elution of the products that have similar physical and chemical properties, such as the boiling point. Well, it is important to mention that the distribution for the pyrolysis could be very similar, and the distribution will be depend on the type of polymer that we are working. For example, for PP, we expect to see aliphatic hydrocarbons from C1 to C25, more or less. And all these hydrocarbons will have pretty similar boiling point. For example, we will obtain different hydrocarbons according to different carbon numbers. So we can have different C6 hydrocarbons, and all of them have similar chemical and physical properties. So it's very difficult to separate just using one-dimensional DC. So for this reason, we want to study the pyrolysis using comprehensive dimensional gas chromatography, because these allow to separate the product from the pyrolysis. And with the separation, we can identify and also quantify the pyrolysis products, which is crucial to guide and develop the mechanism, the microkinetic model, and therefore start up the reactor for the pyrolysis. Okay, so now I want to talk about GC by DC. GC by DC is a technique that combines two different columns with two different mechanisms. And they are connected by the modulator. So I will explain the sample goes through the injection port, then flow through the first dimension column. In our lab, we are working with the first dimension column that separates by boiling point. Then the sample goes to the modulator, which is able to send all these samples from the first dimension to a second dimension column. And the second dimension column that we are using in our lab is a column that separates by boiling point. So as you can see here, this is some explanation about how the DC by DC works. So if we're working with just one dimension column, we will see this X plus Y T. But in reality, we will have two different analytes there, X and Y, because they have similar properties, for example, similar boiling point. We are not able to separate them. But if we send this T
to a second dimension column that has different properties, right? They have different polarity, for example. We were able to see two different peaks with two different retention times. And then we were able to form this counter plot and see all the color distribution for the pelts. So for this reason, it's very important to work with the method development. So for that, with that, we will be able to separate all the peaks. And there's different parameters that need to be studied, for example, color selection, modulator settings, and parameter optimization. It has been found that parameter optimization is one of the most important parameters to separate the peaks in the TC by TC. So, for example, in here we can test different column flow and modulation periods. This is an example of the chromatograph that we obtained for the pyrolysis of PP at 500 Celsius. We were able to identify around 300 peaks here. And we went from C3 to C26. In addition, we identified some monoaromatics. So the resolution in this case is one of our factors to analyze to see that the chromatograph is in good shape. So with this, we can use the resolution that is given by the program that we use to analyze chromatograms. And also, we can use a formula proposed by Perez et al., in which we evaluate the resolution in these two dimensions. So, for example, a bad example of resolution is this peak, and a good example of resolution are those peaks. So we can really differentiate between them. So it has been found that a modulation period of 3 seconds and an overlap of 2 Celsius per minute reduce the percentage with resolution lower than 1. That means we are having a good resolution. Almost all the peaks in the chromatograph are separated. And we can proceed with the identification and the quantification. So for the identification of the products, we have identified almost all these 300 products, which is a lot. And we have grouped them for carbon number and for the type of hydrocarbon that we are working. So we identify alkane, alkenes, cycloalkane, which is very important that it's not widely reported for the analysis of PP, we are obtaining that, but also in the publication, they are using just one-dimensional gas chromatography. So they are not able to separate them. Cyclodiene, and also a small amount of monoaromatics. The main products identified is the C9, propane, so C5, C5 and C6 products, and so on. Finally, with all these projects, we are able to separate the product distribution, the product from the pyrolysis, using a column combination that we have the first column separated by boiling point and the second by polarity. Then we have optimized the modulation period using a 3-second and overlap of 2 Celsius per minute, and we have identified alkanes, alkenes, and aldehydes. I want acknowledgement to the U.S. Department of Energy, the Renee Institute, Ubertile, and the National Agency of Investigation and Development. Thank you. Come on.
Are the cyclohexane or other confirmed with any standard, or is it just matching the M/D profile?
We are, yeah, I understand your question. We are using for the identification of the products, we are using the MIST library. So we are matching the mass spectra for each peak to one mass spectra in the MIST library. Then for the quantification, we are using FID, and for that, we need to use some standards to know the yield of the products. But in this stage, we are just working with the identification. The next step in this work will be the quantification and also see the interaction between different products.
I think for some of the compounds from the environment, we can get only like 40 or 50% confidence in the because I mean you don't get all the fields of environment, and you will sometimes end up matching your field and right. So how can we respond to that?
Yeah, that's a very good question. So for this library, we are working with the match factor and reverse factor. So we are seeing the mass spectra in the literature and the mass spectra that we are having. Also, we are using a very sophisticated system that is allowing us to have a very good resolution in the mass spectra. So we are able to identify them with a very good match factor and reverse factor.
Do you think we can do the same between something like a PLC or PLC together and a different have two different PLC different.
So I'm not familiar with techniques. So I cannot say that we can do the same with those techniques, but at least we cannot do the same using the GC by GC, one-dimensional GC. That is normally used to identify the product from the pyrolysis. It's widely used in the So in that sense, I use this kind of GC by GC will allow us to have a lot of information that we can use then to model the mechanism for the process. No, yeah, you can use whatever you want. Yeah. Also, we have been used for the pharmaceutical industry, forensic, and so on. This is one of the applications which is very new. There is not a lot of regular use this kind of system with to pyrolyze and analyze the policies. Yeah.
Another round of applause for Barbara. And I'd just like to say a huge thank you to all 6 of our graduate student speakers.
I was going to add that I think I speak for everybody in saying that we really look forward to seeing how your research careers evolve over time and what's to become of your life. So thank you all again. That concludes the graduate lightning talks, and I think we adjourn for lunch.
Our next speaker, Dr. Menefee, is also an assistant professor in energy and mineral engineering, and also is a affiliated faculty with the Institute of Energy and Environment at Penn State. And her research is broadly focused on advancing sustainable energy and carbon management systems. Much of this work targets subsurface systems that can be engineered for low carbon energy production and carbon sequestration, which are indispensable to avert the worst impacts of climate change.
Okay, do I have this mic on?
Yes.
Thank you, Mark, for the introduction. I'm excited to be here today. And the slideshow. Okay, so today I'm going to be talking to you about some of the small-scale geochemistry that would enable large-scale management of CO2 emissions within the subsurface, which has really been a major focal point of my research agenda both in the past and moving forward. So just to preface this with a quick baseline, All my work is really predicated on the understanding that climate change is a problem and that it will take a portfolio of all of the solutions that we have at our disposal to properly address it. And so a huge part of this is a huge part of this is transitioning to renewable energy and more low carbon energy sources. There's also broad scientific consensus that really avoiding the worst impacts of climate change will require some extent of large-scale carbon capture and sequestration. And so what we mean by that is taking CO2 emissions, typically from a point source like a power plant or an industrial facility, and injecting them deep underground so that they're permanently isolated from the atmosphere. And so we're basically mitigating our emissions to reduce their impact on global warming. It's not the most glamorous solution to climate change, but that's kind of where we are. And so the subsurface will play a huge role in carbon management, right? Both from the perspective that it's a source of emerging energy technologies for low carbon energy, like geothermal energy production. It's a huge source of energy storage, right? It can serve as kind of a natural battery to support broader deployment of renewables and kind of overcome issues with curtailment and intermittency. And then it serves as a natural sink for our CO2 emissions on industrial scales through carbon sequestration. And so one of the big challenges with engineering the subsurface for these different technologies is that it's really vulnerable to alteration by geochemical reactions between the fluids that we're injecting or extracting and the host rock that we're injecting them into. And what I mean by that is mostly dissolution of minerals that are existing in the subsurface and precipitation of new mineral phases. And the reason this is problematic is that precipitation in particular is notorious for causing wellbores, right? We're referring to mineral scaling is a more common word for it. And so you can block your flow paths in a way that completely shuts down operations. And it's definitely a notorious challenge in the oil and gas industry and will be significant for all of these emerging technologies as well. And so where a lot of my research comes in is looking at trying to understand how these geochemical reactions impact our ability to sequester CO2 in the subsurface, right? So traditionally in most subsurface engineering applications, we're actively trying to avoid any form of mineral precipitation for the reasons I just mentioned. You don't want to completely shut off flow in your system and shut down your operation. But with CO2 sequestration, we can actually take advantage of natural geochemical reactions in the subsurface to promote permanent sequestration through mineral trapping. And so I'll try to quickly explain what that is if you haven't heard of it before. Traditionally, when we thought and looked at CO2 storage, we're talking about sequestering it in these really nice, large sedimentary basins. We have a lot of expertise working with sedimentary basins just from decades of oil and gas industry experience. And they're really porous and easy to inject into. But they're also pretty much chemically inert. And so when we inject the CO2, we are basically relying on the formation to physically contain it underneath some form of impermeable cap rock or seal on top of it. So alternatively, we can target more reactive formations where the geochemistry is more favorable to permanently trap the CO2. So I won't get into a geology lesson, but one of the main targets for this type of trapping are the salt formations, which is the type of rock you would find in volcanically active regions. And so the reason that the salts are advantageous for this is that they're really rich in reactive silicate minerals like pyroxene and olivine, which dissolve rapidly in the presence of a weak acid like CO2. And this dissolution releases divalent ions in dissolution like calcium and magnesium, which can ultimately react with the dissolved CO2 in the pore fluids and precipitate out of solution as a stable carbonate mineral like calcite. And so the advantage of this approach is that you're basically eliminating any leakage risk of CO2 injection underground because you're able to convert it to a stable solid form. It's theoretically going to stay there for thousands of years over geologic timescales. And so I've over the past few years pursued these two, I would say, parallel research directions. One, really trying to understand and predict where and when these types of mineralization reactions occur in the subsurface and how to enhance them for the purpose of permanent CO2 trapping. And then what are the implications of these types of reactions for long-term injectivity and fluid transport in the subsurface? Because like I mentioned before, when you're precipitating a solid phase anywhere, it's going to act to kind of try and block flow. So a lot of this work, I'm not going to go into detail on the methodology just in the interest of time, but a lot of this work has involved core flooding experiments to try to basically recreate reservoir conditions in a lab. So here we're injecting CO2 or another reactive fluid into a real rock under reservoir temperature and pressure conditions. Again, I'm not going to go into the methods. I'll just highlight a few interesting results from all of these experiments I've run over the past few years. And so on the side of CO2 mineralization, we're injecting CO2 into a reactive basalt core to try to promote its permanent trapping through mineralization reactions. We saw that it does actually work in lab settings under realistic reservoir conditions. But we also saw, some interesting effects across our experience where the carbonate minerals that precipitated tend to be very strongly localized structurally. So this is an example of a carbonate mineral that formed from injected CO2 on the surface of a basalt. It was kind of pooling in a vesicle between two fracture surfaces. This is a polymorph of calcium carbonate for anyone who's interested in the mineralogy. But anyway, we found they were highly localized structurally. They really favored smaller pores and vesicles that had the highest amount of reactive surface area, which makes sense. But we also found that the carbonate minerals tended to be strongly localized chemically, where they were really just forming directly on or around the mineral grains that were dissolving to provide the divalent cations that can trap CO2 in the form of these solid carbonate crystals. So the fact that we saw such strong localization, both chemically and structurally on these really small micro scales, really makes the prediction of where these reactions will occur very difficult across the reservoir study. You start talking a lot about the computational sides of this, and I know he's more focused on the mechanics. But chemistry is also really important, and we have these microscale reactions that are kind of idiosyncratic and depend on all these microscale properties and feedback among them. It becomes really difficult to kind of upscale our understanding of how systems work on these scales to a reservoir or basin. So in terms of ways to enhance mineralization, we were somewhat surprised that spiking the system with a buffering agent resulted in a pretty dramatic increase in the extent of precipitation in these samples. And that was surprising because higher pH tends to reduce dissolution rates of the basaltic rock, which is a necessary precursor for all of these precipitation reactions to occur. And so this result kind of showed us that, at least in this system, precipitation is the rate limiting step, and also that more alkaline reservoirs will actually be favorable for these types of mineralization reactions. And then less surprisingly, we found that higher temperature also accelerated the rate and extent of precipitation. This is mostly just attributed to the fact that heat accelerates both precipitation and dissolution kinetics. Okay, so in all of this was just a very high-level overview of a few experiments I did. But in all of the basalt experiments, despite the fact that we saw a lot of precipitation, we never saw any measurable alterations to fluid transport or permeability in our rocks. So that's where the second direction comes in, is trying to kind of create analog experiments where they're really designed to promote enough precipitation that we can start to try to get at these questions of how precipitation impacts fluid transport, especially in fractures, whether that's by completely blocking the fracture and cutting off flow, reducing reactivity just by coating a fracture, or whether there are cases under which crystallization of new precipitates can exert enough stress on the surrounding rock to induce tensile fracturing and essentially propagate new fractures in the system. So again, I'm going to kind of gloss over the methodology in the interest of time. Most of these experiments got pretty gnarly, but basically I ran a bunch of shear experiments in a triaxial core vessel that was positioned inside of an X-ray computed tomography scanner. And so that allows us to take real-time X-ray images to really be able to capture what's going on in real time during these experiments. And basically, I was breaking a shale core in the reactor through direct shear fracturing. So basically, we increase the shear stress on the sample until shear failure occurs. And then at the same time, we were injecting barium-rich fluids into the fracture pathway to promote precipitation of barium carbonate, because that's a very dense mineral and it's highly visible in X-ray imaging. So I'll share a few results from these experiments. We got a very broad spectrum of results across these experiments because we are working with heterogeneous rocks. And so the way that they break, where precipitation forms, all of that is very, we're kind of at the mercy of different properties of the rocks. And obviously we don't have control over how those properties are distributed throughout the samples. So in this first experiment, we generated a fairly narrow fracture, main through-going fracture at least. And it was pretty intricate, the amount of offshoot fractures that formed in this experiment, which I'll show on the next slide. But we got the precipitation of barium carbonate throughout the fracture. I'm not sure how well you can see it out there, but it's all these little white opaque regions in the middle of the fracture. And it's pretty evenly distributed throughout the, or unevenly distributed throughout the fracture network. Despite the fact that in this test we were filling the fracture with precipitation throughout the experiment, and we were also actually increasing the stress pushing in on the sample. So both of those things act to close up the amount of space you have for flow. We actually saw that permeability was maintained throughout the experiment, which suggests that in this situation, the precipitates were basically cropping over the fracture and allowing enough flow paths to be maintained that transport wasn't impacted. These are some scanning electroscopy images from a thin section of the reactive sample. I mostly just threw those in here because I think they look cool, but we did see a lot of the same localization effects that we saw with the basalt work, where precipitation is favoring regions with high reactive surface area. So you get a lot of it in these narrow fracture regions, and especially in more heavily fragmented regions that were generated during the shear fraction, where you have a lot of fresh surface area for precipitate nucleation to occur. So then the last kind of experimental thing I wanted to share was just another one of these experiments that had some kind of contrasting results. So this was an experiment on a different shale sample where we basically just sheared the heck out of this sample. I won't go into detail on all of this data in here, but all of these purple spikes refer to a distinct shear event on the sample where additional slippage and failure occurred. And so you can see this left a lot of very gaping fractures in the sample throughout the experiment. We did see that flow was impacted in this test. Permeability basically took a nosedive from around 200 millidarcies down to 0 in the middle of the test. And that coincided with the onset of precipitation at the inlet of the core and at these kind of critical choke points between the fracture walls. And so the results of this experiment were really interesting to us because we actually calculated that the amount of barium carbonate that formed was much less than in the experiment I just showed you. But because it was forming at more critical locations for fluid transport, it had a much more pronounced impact on flow, which indicates that the spatial distribution of precipitation reactions is really significant and consequential. Again, these are just some thin sections because they look cool. We saw a lot of, again, precipitate localization on calcium-rich mineral grains, and it was more concentrated in fragmented regions. But in general, navigating these thin sections, there is a bit of arbitrariness to where precipitation forms. We did some modeling with this work as well, which I'm not presenting, but it shows that there's a relatively uniform thermodynamic favorability of precipitation across these fracture systems, and yet you only see it in specific locations. And this is just because there's so much complicated defect mechanisms going on that you can't really fully capture in the model. So that's really an area, a future or current and future direction of work for us is trying to be able to develop models that are better able to capture phenomena that would enable us to predict where it's occurring more accurately. Okay, so just to wrap up with a few kind of summary thoughts. Geochemistry is definitely really important for subsurface engineering, especially from the angle of carbon management. Mineral trapping is the most secure form of carbon sequestration that we have right now. But because precipitation in the subsurface has all these mixed implications for long-term fluid transport, there is definitely a limit to how much CO2 we can inject and ultimately mineralize in the subsurface. And it's really hard to quantify that because a lot of times the impact of these geochemical reactions on injectivity depends a lot more on where the dissolution or precipitation reactions occur as opposed to just how much of the mineral is dissolving or precipitating, which is the thing that most models can more readily predict. So really challenging. Precipitation is notoriously painful to study in the lab because you can create all the perfect conditions for it, even in a batch reactor, and you still get no precipitation, or sometimes you get scaling when you don't want it. So definitely an area that still needs a lot of research to be able to kind of feed all of these idiosyncrasies we see in experiments into an actual understanding of mechanisms that we can put into models to more accurately predict how these geochemical reactions play out in different subsurface engineering applications. Yeah, so that's all the content I have. Just wanted to give a shout out to some of the awesome people that I worked with on these projects and our funding sources, and I'm happy to answer questions.
Great, thank you. Questions for Dr. Menefee?
Nice presentation. So the evidence of precipitation that we have in the images shows very clearly tendency to localize by structural features and also mineral composition. I didn't see any evidence of in time. In fact, it was interesting to me to see that there was precipitation on the inlet rather than near the outlet, when we had enough time to precipitate the minerals. So why is that?
That's a good question. I didn't really get into the influence of transport, which is obviously a huge factor here. All of the basalt experiments where we saw the carbonate minerals forming were the PEC line numbers indicate they're dominated by diffusion. A lot of those experiments I was injecting at very, very slow flow rates. And because of the way the fracture systems were kind of etched out, most of the fractures where carbonates were forming were in regions that it was strictly transported by diffusion. So obviously longer residence times are generally advantageous for precipitation because you have more time for the necessary reactions to occur. But in terms of the last experiments on the shale, with how I think this is the one you're talking about, right? With how they're forming at the inlet. This was really interesting because this system was definitely injection dominated. We were flowing at like 1 to 10 mils per minute in these tests. So it was fairly quick introduction of the fluid. And this precipitation occurred within 10 to 20 minutes of the shear fracturing event. So kind of our, I guess, working hypothesis for why it was so quick is just because in this particular test, we were injecting a fluid that was already so oversaturated with respect to barium that it was almost at the point where, homogeneous nucleation will occur in solution. And because, we were directly fracturing it at the same time we were introducing a reactive fluid, it was able to pretty quickly nucleate on these like freshly kind of sheared surfaces. As to why it occurred at the inlet in this experiment, I'm not exactly sure, other than the fact that the way that the shear fracture kind of played out, this was the place where the apertures were the smallest. And so that's, going to be more favorable than kind of these larger areas where you have a higher fluid rock ratio. So I don't know if that addresses your question at all, but yeah.
Other questions? Yes.
Well, thanks for the presentation, very interesting. When we inject CO2 back into reservoirs, it'll be much deeper, different pressures and temperatures. So if you look at temperature and pressure variations,
I did, yeah. All of the CO2 experiments were conducted at 10 megapascals of pore pressure, 20 megapascals of confining pressure, at temperatures up to 150 degrees C. Most of them I would run at 100 degrees C just because it's a little bit hotter than we would expect to see in the subsurface, but it makes reactions proceed on more useful experimental timescales. And so, yes, I would say temperature and pressure are huge, but I did run all of these experiments under kind of similar reservoir conditions. Yeah, so different pressure is not something that I specifically constrained. I wanted to run all my experiments under what we would expect injection conditions and to be in the subsurface, and confining stress that mimics with the static stress at injection conditions. But this is, an example of the influence of temperature. It's not the best images. I didn't include any of the quantitative data here, just for the purposes of time in explaining it and also just, being more illustrative with these kinds of slides. But yeah, we definitely saw a dramatic increase with temperature and the amount of precipitation. So I would say temperature is probably a greater influence than pressure. And it's something that also varies a lot more. I know they did a pilot project of CO2 injection in Iceland, and that was a really shallow reservoir, I think around 20 degrees C. And they still saw precipitation there. But I would imagine, if you're injecting it at 50 to 60 C, you see a much more rapid carbonation process.
Thank you. And very nice presentation, but of course, we would like to have engineers of control, right? So we would like to control the precipitation locations that we really wanted. And it's also going back to Nelson's presentation. What's the scope for doing engineering of control precipitation and selective spots, not like an inlet that we experience today?
Right. Now that's a great question. It's useful for both the CO2 trapping process, especially, if we could control it in a way we could almost seed formations that don't contain these reactive minerals with something where it could precipitate out. And I know it's also something that people are considering is, whether we can manipulate precipitation reactions to create almost a geofence if we're trying to store something in a formation and want to selectively control where we, the boundaries of that plume. Right now, our main ways to control it are either, through temperature, like we inject something that has, a temperature specific coating on it where it dissolves at certain temperatures and, releases something that will precipitate. And so that's, a limited control where if you have very defined stratigraphy and, your geothermal gradient, maybe that's a way to control it. But in terms of carbon mineralization, the reactions are really specific to the mineralogy of your formation. So I would say if it's relatively homogeneous, it's a lot easier to kind of at least predict where you think the mineralization will occur. But yeah, I would say that that's a big outstanding challenge, is trying to kind of take our understanding of how these reactions happen and translate that into some way to engineer them. And that's an area that I'm still working on, especially on the modeling side, but I'm not aware that anyone has, a foolproof solution to it in real systems.
All right. Please join me in thanking Dr. Menefee again. Okay. Dr. Renee Obringer is an assistant professor of energy and mineral engineering and a faculty associate in the Earth and Mineral Systems Institute. Dr. Obringer's research focuses on leveraging data science methods to better understand the impact of weather and climate on critical infrastructure. She's particularly interested in studying climate change impacts on interdependent infrastructure systems.
All right. So thanks for that introduction, and thanks for having me. So today I'm going to talk about just a very broad introduction to some data analysis work and how I use data analysis to better understand the impacts that future climate scenarios might have on our electricity demand, and ultimately hope to use that to gain insights on building resilience in our infrastructure. So the main motivation for my research in general is sort of related to Anne's work on climate change mitigation. I'm really interested in climate change adaptation. And this is a recent figure from the IPCC report from a few weeks ago. And essentially they were looking at these different scenarios and what it might mean in terms of the final warming at the end of the century and sort of what that means for our various activities. So these scenarios range from our worst case scenario, which they call C8. And this is sort of unmitigated warming, no adaptation. And then C1 is our best case scenario. This is where we start to take some of those strategies that Anne talked about to actively not only limit our emissions, but also remove them from the atmosphere. And so what I'm interested in is what these scenarios mean for our electricity system
and broadly speaking, looking at electricity demand. So in order to do this analysis, I focused on this sort of broad topic called predictive modeling. And predictive modeling is also known as supervised learning, but it's really this broad subset of algorithms that can be used to predict some phenomena based off of whatever your input variables are. And it's really powerful, mostly due to the flexibility that we have. So we can use these really more simplistic models, known as kinetic models, such as linear regression. And so that's used very commonly throughout a number of different applications, but we can also start to increase the complexity with these semi-parametric models. So these are closely related to linear regression, but perhaps allow for a bit more flexibility. Think of by calling the cubic or quadratic formulas. But then where I focus on is this final category called non-parametric. These are very sort of like artificial neural networks or decision trees. They're very flexible models, and they really allow for a lot of exploratory data analysis, but also are very good at predicting. And so in particular, I focus on a lot of tree-based models, which is sort of why this flowchart expands. And this is primarily because tree-based models are both very good at predicting, but also very easy to interpret. So this is sort of something that within data analytics, we're always trying to balance. We can have a model that is doing really good at predicting, but it's sort of a black box. We don't know what's going on inside, and that makes it really hard to figure out, to gain insight from that, figure out why our model is doing this prediction, and potentially start to look at what we could change to improve that. And so in particular today, I'm going to talk about a research study that uses this BART algorithm. So this is Bayesian adaptive regression tree, and it builds a number of trees and ultimately aggregates them together. And so this improves upon some issues that we commonly see with decision trees being very unstable, in the sense that if we train it on a certain subset of data, it might be super dependent on that data itself. You might get different models with different data. So by using this BART algorithm, by building many trees and aggregating them together, we actually improve the stability of the analysis. But before I get into the actual results, I wanted to walk through the modeling process, because there are a lot of pitfalls that can be associated with this data analytics. Particularly, one of the major issues is in the data collection. So if you collect data that is, for lack of a better word, garbage data, your model is going to be garbage as well. So you need to make sure that the data you're collecting, and most of the time I'm not actually doing the data collection, I'm using publicly available data sets. So I need to go through and make sure that the people that did do the data collection did their due diligence, that this is all accurate and has been verified. But within the data collection, there are two key pieces of data that I'm working to collect. One is the response variable, or sort of what you're hoping to predict, the Y or independent variable, or dependent variable, sorry. So in my work, it's often electricity demand. And then I'm also collecting predictor data. So what I'm using to make that prediction, and in this case, is often these climatic variables. And then there's often some pre-processing phases, so maybe aggregation, spatially or temporally, doing some trending. But the bulk of the analysis happens in these green squares. And this is where another sort of challenge associated with data analytics gets solved to the best of our ability. And that's using what's known as cross-validation to first train a model and then to test it or validate it. And so what we do is we split the data into a training set and a test set. And so we build a model based off of our training data set, and then we test it to see how it does on data that it hasn't seen before. And we do this iteratively, so that within each sort of iteration, a different group of data is being used as a test set. And so this allows us to improve the bias of our model, so make it so that when we use a set of training data that is not solely dependent on that data, that we can actually use outside predictions to actually get an accurate prediction. And then the cross-validation sort of increases the stability. So you can imagine that if you train a model for electricity demand on data from the 1970s, and then try to use it to predict data from 2022, you're not going to have a very good prediction because the way that we use electricity has changed in the last 50 years. So what we want to do is we want to make sure that our training is takes the whole data set, but also that we're iteratively doing these different test sets to make sure that we can predict the entire range of data. And then there's also some other sort of measuring model diagnostics, figuring out what the important variables are, and then ultimately enhancing the analysis. So I use this this modeling process in all of the work that I do, but today I'm going to talk about this research goal one project, which was to look at the air conditioning in the US. And so this was recently published earlier this year, and our goal was to first model the observational relationship between climate data and air conditioning use, and then later project that into the future. So what we did is, following that modeling process, we collected data. Our response variable here is air conditioning demand, and our predictor data is the series of weather variables that we can collect from publicly available weather stations. And then we went through the training and testing process. And the result is this prediction of air conditioning use as a function of the external climate conditions. And then when we went to actually project that work, we replaced our weather data with data from the CMIP-5 suite of climate models, and specifically looking at this RCP 8.5, which is this blue curve here. And in the previous iteration of the IPCC, they were using, so they're currently using CMIP-6. This is the previous iteration. RCP 8.5 was our worst case scenario. It's now called C8. But it's essentially unmitigated warming. And in fact, it actually might be a little bit worse than this is usual. So if we change nothing, we might actually end up a little bit lower. But this is the worst case scenario. So really sort of digging into what is the worst possible future in terms of our air conditioning demand. And then because of the projection, I don't actually have future air conditioning data to compare it to. So we're using this previously trained and tested model that was shown to be accurate, and then using that to insert new input data and saying what is the possible future then. And specifically, we did this analysis for temperature thresholds. And so instead of looking at what will happen after 2030 or 2040, we looked at what will happen after 1.5 degrees of warming or 2 degrees of warming above pre-industrial levels. And this just helps situate sort of this analysis within larger international discussions on where we should try to limit our warming, as well as what the climate impact community is really moving towards in terms of that analysis, because it allows for a bit more flexibility. Instead of saying hard deadline, this is what will happen in 2030, we're saying, we will likely surpass 1.5 degrees 2030, 2035, and when that happens, this is what we would expect. So, that is interesting.
Let me see if I can rotate that really quick. I don't know how that happened in between, like there we go. Yeah. And then make sure the display settings go back to there. All right.
So this is what our results. So we're doing this across the US, and we're looking at an average household within each state. And what the plot is showing is, in the background, we've got the baseline electricity use for air conditioning on an average household basis. And then the blue bars are showing the median % increase after 1.5 degrees, And then the red is the median after 2 degrees. And so we can see that just in general across this country, most places are seeing an increase. Even places in the Pacific Northwest where we haven't traditionally used air conditioning, there's a slight increase in household. But I want to draw attention first to Arizona. Because Arizona has the darkest background. They're the highest per household user, which makes complete sense since Arizona is largely desert. And so what we're seeing is that our model is showing that after 1.5 degrees of warming, a median increase in 6% of the household level air conditioning use. And after 2 degrees, so there's another 0.5 degree of warming that increases to close to 10%. So we're definitely seeing these relationships that we expect intuitively when we think about how each of us uses air conditioning. If it's hotter outside, we turn off the air conditioning. And so we expect Arizona to get warmer, so it makes sense that what we're seeing. But depending on sort of what this means for the average household, this could actually be quite a bit of additional electricity that needs to be supplied through our grid. But I also want to focus in on Indiana and Ohio, and more broadly the Midwest follows a similar trend, where we have a really fairly low increase after 1.5 degrees, less than 4%. Maybe not ideal in terms of just looking at this climate impact, but it's not the worst that we've seen. But after this 2 degrees, just a 0.5 degree more warming, suddenly our model is looking at 4 times the percent increase, up to 13%. And this is actually one of the, I think it might actually be the highest percentage increase